Nodal analysis is another common method of analysis for simplifying circuits. Nodal analysis also has two types, the general approach and the format approach. And again, format approach is a shortcut like the mesh analysis format approach. So let's start with the general approach. And remember, nodes means junctions. Nodes and junctions, they're the same thing. Basically, any point where more than two branches meet, that is a node or a junction. Now, step one is to consider the ground node to be 0 volts. And this is not compulsory, this just makes life easier. See this red mark down here? This is the ground node, and we will consider this to be 0. And since we are considering one of the nodes to be 0, then comes steps number 2. So number of nodes equal to total nodes minus 1. Like I said, since we are considering one of the nodes to be 0, the number of nodes we will be analyzing will be total nodes minus 1. Now here we can see the total nodes was 2. One node up here and one node down here. But since this one is being considered 0, so the number of nodes we will analyze is just 1. This V1. And we will assign each node to be a voltage V1, V2, V3, etc. So we are assigning this node as V1. If we had another one, it would be V2, another one would be V3, like that. Now, step 4 is to apply KCL for each node. And when there are other voltage sources in the branch, we consider the node, the assigned node, to be the source. So we will consider that the current is exiting the assigned nodes. Okay, like you can see here, I1 and then I2, these are all exiting the current nodes. But I3 here, not I3, this will be I. This is actually wrong. It won't be like this. We cannot assign anything here because current source is already assigned here. The direction is already given upwards. Already given upwards this way. So that means this current source is entering the node. Okay. So when current sources are given, their direction will be followed as it is given, if it's upwards or downwards, whatever, exiting or entering. But except that every other node, we will consider that the current is exiting the node. This just makes life easier. Okay. And that's it. Now we apply, after applying we apply KCL to each node and solve the resulting equations. And again, the number of equations will be equal to the number of nodes we are analyzing. Okay, let's start with this. There is only one node, so we'll start with V1. First, let's apply KCL. So applying KCL, we can see that I1 and I2 is leaving, I1 is entering. So just I is entering. So I is equal to current entering is equal to current leaving. So I1 plus I2. Okay. Now let's apply Ohm's law. So I is just I, it will be 1 ampere. Now I1 is V1, but there's another source here. So it will be V1 minus E. Now why minus? Because as you can see, this current is entering the positive end. So I just like to assume the opposite. So if it's entering the positive end, it will be minus. You can assume that if it's entering the positive end, it will be plus, but you have to stay consistent for every node. V1 minus E over R1 plus I2 is V1. There's no minus. You can write minus 0, but you don't have to because this node is 0. And over R2. Okay, now let's plug in the values. So 1 is equal to V1 minus E is 24 volts over R1, so 6 plus V1 over 12. Let's take LCM. 1 is equal to, so we have 12 here. So up here we have 2 V1 minus 24. This is just a normal LCM plus V1. Okay, let's go to the next page. Let's copy all of this. Okay, it won't copy. Come on, just get copied. No, it won't copy. Anyways, we can just remember 1 is equal to 2. 1 is equal to 25. What was it again? 2 into v1 minus 24 plus v1 over 12 plus v1 over 12. Let's take 12 to the other side. So let's actually bring this to the left side and remove the bracket. So 2v1 minus 48 and plus v1 is equal to 12. So we have 3v1 is equal to 12 plus 48. 12 plus 48, that's 60. So v1 is equal to 60 over 3, that's 20 volts. So that's our answer for v1. Now let's do another one. Okay, here we have two ground nodes, will be 0, 0. And let's assign these nodes with the red marker again. So this will be one node. This will be our v1, and this will be our v2. Now for v1, current will exit here, and exit here. So I1, this will be I, and this will be I2. For v2, current will enter here, exit here, and exit here. This will be I1, and I2. Okay, so let's start with v1. I won't write the I's, I'll just go directly to the Ohm's law version of it. But yes, we'll be applying KCL now. So for node 1, okay, this is for node v1. For node v1, let's see what we have. v1 minus, this is basically for I1, so v1 minus E. I'll just directly plug in the values. v1 minus 64. Again, minus because I'm assuming that entering through plus means it will be minus. So v1 minus 64 over 8. And then that is exiting. We have another exiting, which is I2. So I2 is v1 minus v2. And now notice this important thing. So v1, I2 from v1 is going this way, and I2 from v2 is going this way. So they're clashing here. And so we'll take the resultant, and resultant will be, when we are analyzing node v1, it will be v1 minus v2. And when we'll be analyzing node v2, it will be v2 minus v1. Okay. Whichever node we are analyzing, that node is the king. So v1 minus v2 over r2, so that's 4. That is the current exiting, and current all the currents are exiting from node 1. So we'll have plus I, so that's 2 ampere, equal to 0. Okay, let's do the LCM. Instead of taking LCM, we can do another thing, which is separate them. So v1 over 8 minus 64 over 8, which will be 8. Right here, 64 over 8 will be 8. And then plus v1 over 4 minus v2 over 4 plus 2 is equal to 0. So v1 over 1 over 8, v1 times 1 over 8 plus v1 times 1 over 4 minus v2 over 4, and then minus 8 plus 2, so that's minus 6. I send it to the right side, so plus 6 there. Now we add the V1s up, so 1/8 plus 1/4. We have V1 times 3/8. I can just use the decimals. So we have 0.375 V1, 0.375 V1 minus 0.25 V2, 0.25 V2 equal to 6. Okay, so that's our equation, first equation for node 1. Okay, now let's make equation 2 for the second node V2. Now for V2, I is entering, I1 is leaving, I2 is leaving. So we will have I is equal to I1 plus I2, right? I1 plus I2 is equal to I. Let's just wait. So I1 plus I2 is equal to I. Now I1, where's I1? I1 is V2 over 10. V2 over 10. V2 over 10 plus I2 is V2 minus V1 over 4. From here, V2 minus V1 over 4. That's V2 minus V1 over 4. Sorry. Equal to I1 is just 2 amperes. 2 ampere. Okay, again, let's break that down. So 1/10 is 0.2, I think. 0.1. So 0.1 V2 and then plus V2 over 4, right? V2 over 4 will be 0.25 V2 again. So 0.25 V2 minus V1 over 4, so 0.25 V1 is equal to 2. Let's bring V1 to the front, so minus 0.25 V1 and then 0.1 plus 0.25. So 0.35 plus 0.35 V2 is equal to 2. That's our equation 2. Okay. Now we have two linear equations. Again, we can plug it in the calculator and solve it. So 0.375 minus 0.25 plus 6. And the other one is minus 0.25 plus 0.35 2. So we have V1 is equal to 37.82 volts and V2 is equal to 32.73 volts. That's our answers. Okay, we have another practice here. Now this node, this network has, let's mark the nodes. Okay, so this ground node we'll consider to be 0. Then this node will be our V1 and this node will be our V2. So again, 2 nodes. Now current is entering this way, 4 amperes, and this will be current exiting, again current exiting, and this will be again also current exiting, 2 amperes will be exiting. Okay, that's our marking. Now let's start. Let's make the equations. So for node V1, we'll have current exiting will be V1 over 2 R1, right? Plus V1 minus V2 over R3, so 12. That's the exiting current, and entering is 4 amperes. Okay, now let's arrange that. So 0.5 V1 plus, so 1 over 12 so plus 0.083 plus 0.083, that does not look good. 0.083 V1 minus again 0.083 V2 is equal to 4. Okay, now let's simplify that. So 0.5 plus 0.03, so 0.583 V1 minus 0.083 V2 is equal to 4. That's our equation 1. Now for V2, equation 2 will be, so 2 amperes is exiting, all the currents are exiting from V2. So we will have V2 minus V1 over 12 plus V2 over 6 plus 2 amperes is equal to 0. Okay, let's take that to another page. Hopefully it gets copied. Good. Alright, now so V2 over 12 will be again 0.083 V2 minus 0.083 V1 plus also 1 over 6 0.167 V2 plus 2 is equal to 0. Okay, now let's arrange it. Bring V1 to the front. So minus 0.083 V1 plus 0.083 plus 0.167. So 0.25 plus 0.25 V2 equal to minus 2. That's our equation 2. Alright, now let's solve these two linear equations that we got. So 0.583 minus 0.083 to 4, and then minus 0.083 plus 0.25 minus 2. Okay, so we get V1 is equal to 6 volts approximately, and then V2 is equal to minus 6 volts approximately. Okay, now we have a new concept, supernode. Just like supermesh, where we encounter a current source without a parallel resistor, supernode is used when we encounter a voltage source without a series resistor. And the steps are similar. First we assign node voltages here, like we used to assign loop currents in mesh analysis in supermesh. So in supernode we assign the node voltages first, and then we remove the voltage source in our head. For the first one, I'll redraw the circuit for the sake of simplicity in explanation, but removing it in our head is much faster. That's the standard. Okay, we have another resistor up here, and then a short circuit. Now remember, when we remove voltage sources, we get a short circuit, and when we remove current sources, we get an open circuit. Okay, so here we removed a voltage source, so we have a short circuit. I have redrawn it with a short circuit. This is the short circuit. Now, as seen in this image, V1 and V2 were already assigned. So this node was V2 and this node was V1. But now we can see we have a direct connection between V1 and V2. No obstruction in between, right? So we will form an equation using both V1 and V2. Now let's see. So let's assign the currents first. V1. This current is obvious, just entering V1, and one will be leaving here, and V2 one will be leaving here. This is already leaving V1. But this super node, we created here. Super node will have a current that will exit through V1 and then go through here, and come back to V2. Okay, this is just according to the direction we are assuming. Okay, so we can see that this current is exiting V1, right, and again entering back to V2. Let me assign the currents in the image for some easy understanding. Okay, so we'll have I1 here, okay, and we will have this 6 ampere entering here. Then here we will have I2 exiting V2, and we will have I exiting this 4 ampere. Okay, 4 ampere. And then the supernode current that was created here, the current from the supernode will go like this. Okay, it will create a loop and come back here. Let this be I3. So we can see that I3 is exiting V1, right? I3 is exiting V1, but it's coming back and entering V2, right? So we will have this I3 showing up twice in the equation. Now let's make the equation. So what do we have here? We have current entering. Let's write that. So I in is equal to I out. Now what are the currents entering? 6 ampere is entering. 6 ampere is entering V1, and again I3 is entering V2, right? So plus I3. Now what are the currents exiting? I1 is exiting, okay, then I1 is exiting V1, and then I2 is exiting V2, then 4 amperes is exiting V2, again I3 is exiting V1. So here I3 showed up twice. Now since both are plus plus, we can just cancel it out, throw it out. Okay, now what do we have here? Let's bring I1 to the front. So I1 plus I2 is equal to 6 minus 4, so 2 amperes. I1 plus I2 is equal to 2. Let's take this to a new page. Okay, so what is I1? I1 was this, so V1 over R1, that's I1. So V1 over R1, which is 4 plus I2 is V2 over R2, so 2, V2 over 2. V2 over 2 is equal to 2. Now we have 0.25 V1 plus 0.5 V2 is equal to 2. That's equation 1. Now for the second equation, we will establish a relationship between the two nodes and the voltage source. So we'll place the voltage source back if we have to draw it, but we'll place it back in our head as it was here. We won't draw it. Now we have to establish a relationship between E V1 and V2. Okay, now we know that for V1 and V2 we take it's a resultant, right? We do V1 minus V2, right? And the resultant. Now E is in the place of the resultant in the middle. So we can write that V1 minus V2 is equal to E. That's it. Now we have an equation. Let's place the values. V1 minus V2 will be as it is, and E is how many volts? It's 12 volts. So 12. Now we have equation 2. So now we have two linear equations. Let's plug in the values. So 0.25 plus 0.5, then 1 minus 1. Oh wait, 0.25 plus 0.5, and then 2, and 1 minus 1, and 12. Okay, so now we have the answers. I'll write them here. So V1 is equal to 10.67 volts, and V2 is equal to minus 1.33 volts. Minus 1.33 volts. Okay, now we have another super node question. So we have two voltage sources and one current. So no current is just I loop current, but we won't use that. And if you look carefully, this circuit is actually the same as, wait, I'll bring that image. So these two images are actually the same. Okay, here this current source has just been converted to a voltage source. The numbers are not the same, obviously. Just the format and the arrangement of the circuit of the network is the same, just with source conversion. So this is in current source form, and this has just been converted to voltage sources. The rest are the same. Now let's get rid of this. Okay, so we have V1 and V2 assigned here. Now we will remove the, actually we don't even have to use supernode here. I don't know if we can even use supernode, because this is very easy. It's easy to do by converting, source conversion. So the image I just showed, okay, how we solved this in the previous video in mesh analysis, we will turn this into this. Okay, how? So we have, using source conversion, we have 8 volts and 2 ohm in parallel to 8 volts. So the current source, if we convert it to current source, the direction will be this way, because positive for 8 volt is on the top, and we will have a resistor in parallel. Okay, so this will be 2 ohm as it is, and this will be I is equal to V over R, so 8 over 2, it will be 4 amperes. And then this resistor will be the same, so 12 ohm. Okay, and then 12 volts will again be converted to a current source with this direction, because the positive side is downward in the voltage source, and there will be a resistor in parallel with it, which will be this R2, so 6 ohms. Okay, 6 ohms. And here we have the same circuit. Okay, this circuit is equal to this with just different sources, and this will be 12 volts, so I is equal to V over 12 over 6, so it will be 2 amperes. Okay, so it's the same, just with converter sources. And the way to solve this is the same process how we solved this one in the previous video. So try to solve it by yourselves and check this out if you cannot solve it. Now we'll move on to another question. Okay, node analysis format approach. So like I said, format approach is the shortcut for node analysis. It's the same steps. First we assign the voltages. So let this be V1, assign the nodes, nodal voltages, and V2. Now this current is exiting, I1. This is also exiting and exiting. This is entering, exiting, exiting. Okay. Now let's apply format approach. So just like with mesh analysis, we'll first take our nodal voltage, so V1. In mesh we took our loop current 1. Here we are taking node voltage 1. So V1, open bracket, put all the resistors. So 1 over, we have 1 over 6, 1 over R1, so 1 over 6. Okay, and then we have plus 1 over R3, so 1 over 3. Okay, and then minus, we put V2 and whatever resistor is in relation with V2, between V2 and V1. So we can just write it to 1 since there's only one resistor in relation. So V2 over R3, so there will be 3, equal to sum of all the sources connected to V1, which is just I1, so 2 amperes, just 2. Okay, that's our first equation. Let's simplify that. So 1 over 6 plus 1 over 3, we have 1 over 2, so half, 0.5. 0.5 V1 minus, what's 1 over 3? 0.33 V2. 0.33 V2 is equal to 2. So that's our equation 1. Now let's go to the second node for equation 2. Again the same way, but we'll bring V1 to the front with a negative sign, just as in mesh analysis. So V1 over R1, R3, because that's the only one between V1 and V2, so 3 ohms. Now plus V2, open bracket, and all the resistors, so 1 over 3 plus 1 over 4 from R2, 1 over 4, equal to all the sources connected to V2, which is just 3 amperes. Wait a minute. In the first equation, we had I1 or 2 ampere exiting V1. So exiting means it will be a negative here, okay? Exiting means negative. And in the second node, we see I2, 3 amperes is entering the node V2. So it will be positive, so 3 amperes here, okay? Now let's simplify. 0.33 V1 negative 0.33 V1 plus, let's add them up, 1 over 3 plus 1 over 4, so 0.583. 0.583 V2 is equal to 3. So that's our equation 2. Now plug it in the calculator. 0.5 minus 0.33 and minus 2, then minus 0.33. This doesn't look like a proper minus, and this too. Okay, so minus 0.33 and plus 0.583 equal to 3. Okay, so we have V1 is equal to 0 minus 0.96 volts, and V2 is equal to 4.6 volts. That's our answer here. Let's move on to the next question. Okay, Again, step 1, assign the voltages, nodal voltages. So here will be V1, then this will be V2. But this looks familiar. It's the same question. Why did I put it twice? Okay, let's ignore this. Here we have a new question. So let's assign the voltages. Nodal voltage V1, nodal voltage V2. Okay. So I think the question wanted us to find V3, the voltage running through 3 ohms. But for practice, we'll just find all the voltages. And the voltage running through 3 ohm will be just V2. But we'll find V1 as well. Okay, so wait. Mark the direction of the current. So exit, 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 again exit, exit, all exits. Okay, so V1 for node V1. So V1 minus 8 volts entering through plus, so it's minus over 2 ohms. Then plus V1 over 4 plus V1 minus V2 over 6 is equal to 0. Now let's simplify. So V1 over 2, 0.5 V1 minus 8 over 2, so 4, plus V1 over 4, so 0.25 V1, then V1 over 6, what is 1 over 6 again? 1 over 6, so plus 0.167, 0.167 V1, then minus, continue down here, 0.167 V2 is equal to 0. Now let's arrange that. So we have 0.5 plus 0.25 plus 0.167. So we have 0.917 V1. And then we have minus 0.167 V2 is equal to 4. So that's our equation 1. Now let's get equation 2. So V2 minus V1 over 6. V2 minus V1 over 6 plus V2 over 3. So plus V2 over 3 and then plus V2 minus, it will be V2 plus 1 here, okay? Because current entering through the positive and negative side. So we put a plus in the equation. So V2 plus 1 over 10. So V2 plus 1 over 10 is equal to so all exits are equal to 0. Right. Now let's simplify. So V2 over 6, so 0.167 V2 minus 0.167 V1 plus 0.33 V2 plus V2 over 10, so 0.1 V2 plus 0.1. Let's just send that to the other side. So equal to minus 0.1. Okay. Now bring V1 to the front. So minus 0.167 V1. 0.167 V2 plus 0.33 plus 0.1. So plus 0.597 V2 is equal to minus 0.1. So that's our equation 2. Now let's plug in the values. So we get the values V1 is equal to 4.56 volts, and V2 is equal to 1.10 volts. Okay, done. Now let's do another one for practice. Let's assign the nodal voltages. Okay, so we have 1 volt here. This will be V1. This will be V2. So we have 3 nodes here, V3. And the currents will be exit, exit, and exit. So it will be entry, exit, exit, then again exit, exit, and exit. So let's start with V1. For V1s, using the format approach. So V1 over 1 over 2 plus 1 over 2 plus 1 over 5 minus V2 over 2 is equal to 0. There's no sources for V1. Okay, let's simplify that. 1 over 2 plus 1 over 2 plus 1 over 5. So V1 1.2 V1 minus 0.5 V2 equal to 0. That's equation 1. And now for V2, again format approach. So V2 over, wait a minute, for format we will go minus V1 first. So minus V1 over we have to consider that this is not a node. We can consider it as a node, but we are not. So V1 and V3 has a relation here, this way and this way. We did not consider that here. Let's erase all of this. Come on. Okay, so V1 again, V1 over 1 over 2 plus 1 over 2 plus 1 over 5 plus 5. So 1 over 10. Okay, 1 over 10, that's it. Minus V2 over 2. Then again minus V3 over 5 plus 5, this 2. So 10 equal to 0. No sources in V1. So this again becomes, so this becomes 1.1. 1.1 V1 minus 0.5 V2 minus 0.1 V3 is equal to 0. So that's equation 1. Now for V2, again first we bring in V1. So V1 over 2, then plus V2 over 1 over 2 plus 1 over 2, then minus V3 over 1 into 1 over 2. This 1 over 2, one is from this one and one is from here. And minus V3 because V3 times 1 over 2 because there's only 2 ohms between V2 and V3. Okay, equal to 3 ampere entering, so plus 3. Now let's simplify this. So we have minus 0.5 V1 plus V2, half plus half is 1, minus 0.5 V3 equal to 3. So that's equation 2, not 1. Equation 2. Now we will have another equation for the node V3. Let's get a new page. Okay, so for V3 it will be let's bring in V1 first. So minus V1 over 10, because V1 5 and 5, that's the relation between V1 and V3. So minus V1 over 10, right? And then minus V2 over 2, that's the only one between V2 and V3. So V2 over 2, and then plus V3 over times 1 over 2 plus 1 over 4 plus 1 over 10. So 1 over 2 plus 1 over 4 plus 1 over 10 equal to, are there any sources? No sources for V3, so equal to 0. Okay, now minus 0.1 V1 minus 0.5 V2 plus 1 over 2 plus 1 over 4 plus 1 over 10. That's 0.85 V3 plus 0.85 V3 is equal to 0. That's our equation 3. Now we have three linear equations. Let's plug them in the calculator. So we get V1 is equal to 3.68 volts. V2 is equal to 7.2 volts, and V3 is equal to 4.65 volts. 4.65 volts. Okay, so that's all for mesh analysis. Sorry, nodal analysis, not mesh.